Hello all, and welcome to this next session in this course, Pre-Business School Statistics. So this entire second week has been more about, let's say, random variables, and then we started with probability ideas. Then how do you connect probability ideas to random variables? And then in the last session we talked about some discrete random variables, if you again remember vaguely. So we started the session with Bernoulli random variable, then binomial, Poisson, and right towards the end of last session we somewhat revised very briefly a couple of other discrete distributions such as geometric, negative binomial, etc. Now before we begin with discussing something which is called as a normal random variable, and by the way normal comes from a family which is continuous. So now we are shifting attention to continuous random variables from discrete random variables. But just before handling normal random variable, just a small disclaimer that why are we kind of discussing all these distributions. So again, if you remember vaguely from the last session, I gave a small comment that if you are collecting a random data, if you are collecting a few observations, then that data set or the set of observations follows some distribution. Okay, so then it makes all the more important that we have to find out that what distribution sort of fits the data set that you have. So would that be binomial, would that be Poisson, or if you have a continuous distribution setting, then would that be normal, exponential, etc. Okay, so in both these headings, discrete versus continuous, so in literature we have hundreds of different distributions, and again like I said, people go on extending, let's say they go on extending the parameters, something like that, and then they try to make distributions more and more flexible so that the distributions are able to fit real data a bit more in a better manner. So now here, which is a very standard distribution which people use quite often, is called as a normal random variable or the normal distribution. And again, like I said, the normal distribution is a classic example of a continuous distribution. Now again, before we start with the normal distribution, again just a very quick refresher as to what you mean by continuous random variable. So a continuous random variable means that if x is a continuous random variable, then the range of x belongs to certain interval or union of disjoint intervals. And again, the last session we gave several examples, as a temperature, age, height, weight, salary, income, etc. So all these are continuous variables. For example, if you take temperature or rainfall data, then temperature can also take decimal values. Alright. So temperature need not be recorded every time in discrete values, and hence it makes temperature as a continuous random variable. Okay, so before we begin with any of the nuances of a normal random variable, now this function that you see in front of you is nothing but the PDF of a random variable. Now again, a very small typo here, so it should be PDF because now we are talking about a continuous random variable rather than a discrete random variable. So again, just to remind all of you that if you have a discrete random variable, it's called as PMF or probability mass function, while if you have a continuous random variable, it's called as PDF or probability density function or probability distribution function. Alright, so a random variable x is said to follow a normal distribution with two parameters, so mu and sigma square. So mu and sigma square are a couple of parameters under a normal distribution. Now again remember that any distribution contains certain parameters. For example, if you go back to binomial, then binomial contain two parameters n comma p. If you focus on a Poisson distribution, contain a single parameter lambda, etc. etc. Okay, so the moment you talk about any distribution, be it discrete or continuous, it should contain couple of parameters or more. So for example, here the normal distribution contains two parameters, mu and sigma square, and this is more like a statistical notation. So we say that x follows a normal distribution with parameters mu comma sigma square. Now immediately before we look at the PDF of a normal distribution, this mu is nothing but the mean of a normal distribution directly, and the sigma square is nothing but the variance. Okay. So in general, if x follows a normal distribution or if your real data follows a normal distribution, the average is given by mu and variance of the real data is given by sigma square. Now again remember one more thing, that mu and sigma square are population quantities. So maybe down the line in the next week when we will talk about estimation, then again we will say that how do you estimate these parameters. Okay. So a very standard assumption that we all make is that any parameters are assumed to be unknown since they belong to the population. So for example, here both the parameters mu and sigma square are assumed to be unknown, and hence based on whatever data set you have to estimate both mu and sigma square. Okay. Anyways, but then now the next thing which is important is to talk about the PDF of a normal distribution, and this is the PDF of a normal distribution given by f of x. Again, slightly technical, but then I'll try to elaborate a couple of points here. So, it's given by 1 by sigma under root pi. So, sigma is outside of the under root. So, 1 by sigma under root pi, and then you have this e to the power minus x minus mu whole square divided by 2 sigma square. So, this e is nothing but the exponential function, and then e raised to the power is the entire thing in the exponent. So, minus x minus mu whole square divided by 2 sigma square. And one more important point to note here is that any normal random variable can lie anywhere on the entire real line. So, from minus infinity to infinity. Okay, make sense? Now, a single point to understand here is that let me fix a value of mu and a value of sigma square. So, if you fix a value of mu and a value of sigma square, can you give me a f of x function corresponding to those values? Answer is yes. Okay. So, for example, let us say if I fix mu to be 0 and sigma square to be 1, then what would be the corresponding density? So, you can see clearly that if mu is 0, this would be minus x square, and then since sigma square is 1, it will be minus x square by 2. Okay, and then of course this constant will reduce to 1 by under root pi, and then sigma is 1. Okay, so again, depending on what values mu and sigma square take, the density sort of changes slightly. Alright, now how does a normal PDF plot look like? So again, the exact same PDF we had on the previous slide. Now depending on the values of mu and sigma, so like I said, if you fix a value of mu to be 0 and a value of sigma to be 1, then again this would be the corresponding density, isn't it? And then this curve that you see in the blue is nothing but the density curve of the corresponding normal distribution with mean to be 0 and sigma to be 1. Okay. So again, couple of very interesting points here, that this density is kind of symmetric, and this is a very standard way of, or rather a very standard shape of any normal density curve. It's kind of bell shaped. Okay. So symmetric or bell shaped. Bell shaped is a much more slightly standard name to talk about the shape or the behavior of a normal density curve. And the value that you see right in the middle is nothing but 0, and then almost all the data lies between these two limits. So, can you see that? So, between minus 3 and 3. So, very soon we will talk about a rule called as empirical rule, and then I will try to elaborate a bit more on this fact. But then the idea about this slide is just to tell you the density curve or the behavior of any normal distribution, particularly when we fix mu to be 0 and sigma to be 1. Now again, like I said, if you bring in any other values of mu and sigma, you can create the f of x function and simply plot the f of x function based on values that x can take, and then again you will see that the curve has to be symmetric, but then the only thing is the center point or the midpoint won't be 0 there, but ideally the midpoint would be nothing but mu there, because again remember that mu is nothing but the mean, right. So in this particular case, since mu is 0, we have the midpoint at 0. But then otherwise, if mu takes any other value, let's say 5, 10, 15, 20, whatever, then you will still have a symmetric curve, but then this midpoint would be at that point mu. Alright, so now going a step ahead, so we want to quantify what exactly are the mean and variances of a normal distribution. And again, like I said, the parameters themselves are nothing but the mean and variance functions, or rather the mean and variance parameters of a normal distribution. But again, if you want to apply the formulas, one can do it. So in order to find out the expected value or the mean function of a normal variable, we have to take the expected value of the random variable. And again, if you vaguely remember the formula of taking, or rather finding the expectation, it's nothing but integral x into the PDF dx over the entire range of x. Now since the entire range of x is minus infinity to infinity, we have integral from, or rather over those points, and then x into the PDF function. Now this f of x is nothing but the PDF function we saw on the last slide or the one before that. But then what you do is you simply integrate x into f of x dx, and then finally one can actually show that the answer reduces to simply mu. Now on the other hand, what would be the variance function? Variance function, if you use the formulas, is nothing but expectation of x square minus mu square, isn't it? So expectation of x square minus e of x whole square. And now how do you find out e of x square? So again, simply replace x square in terms of x here inside the integral. So you integrate from minus infinity to infinity, and then x square into the PDF dx, and minus mean square. So since mean is mu, I will simply take mu square, and then one can do this mathematically and then sort of prove that this sort of reduces to nothing but sigma square. So again, just to remind that mean reduces to mu, whereas my variance reduces to nothing but sigma square. Okay. Now a very interesting property about a normal distribution, that if x is a normal variable or a normal random variable with mean mu and variance sigma square, Then let's say if I make a very small and very easy transformation. So what exactly is the transformation? Transformation is y equals ax plus b, where a is a constant and b is also a constant. Okay. So again, just to summarize, you have x which follows a normal distribution with mean mu and variance sigma square, and then what you're doing is you are making a transformation something like this. So y equals ax plus b, where a and b are constants. So it so turns out that the distribution of y is also normal with mean a mu and variance a square sigma square. Okay. So mean of the random variable y becomes a mu, a into mu, and variance of the random variable y becomes a square into sigma square. Okay. So these are a couple of properties. It will be a good idea if you sort of keep such properties in mind related to a normal variable. So if x is a normal variable, then any linear function for that matter, because ax plus b is a linear function. So any linear function where a and b are constants, and if you are transforming x to any linear function, then any linear function is also normally distributed, but the only thing is that mean and variance would change according to these ideas. So mean would become a mu and variance becomes a square into sigma square. Alright, now the other side of the coin is, what do you mean by a standard normal distribution? So many a times it's always easier to work with a standard normal distribution, and then you'll see why exactly. So a standard normal distribution means nothing but if you start with a normal variable which is x, so x follows a normal distribution with mean mu and variance sigma square, then if you make this transformation instead, so z equals x minus mu divided by sigma. So essentially what you're doing, you're subtracting the mean and dividing by the standard deviation, isn't it? So by the way, sigma square is the variance, so sigma is called as the standard deviation. So you're kind of standardizing the normal variable. Okay, so this process is also called as standardizing the normal variable. So you have alternative definitions for that. So standardizing, normalizing. Okay. So here what I am doing is that if you start with any normal variable having some mean mu and variance sigma square, then you have to standardize the normal variable first. So subtract the mean divided by the standard deviation, and then it so turns out that the variable z follows a normal variable with mean 0 and variance 1. So such a random variable is called as a standard normal random variable. So standard normal is more like a very specific case of a normal variable where mu is 0 and sigma square is 1. And why does mean become 0 and variance becomes 1 is kind of clear from this transformation, right? I mean, if you are subtracting the mean from x, okay, so in the numerator what are you doing? So you're kind of subtracting the mean from a initial random variable x. So if you subtract the mean from a random variable having a mean mu, right, then the overall mean has to be 0, isn't it? And similarly, you are dividing by the standard deviation, so the variance reduces to 1, kind of. Okay. And again, if you take the earlier f of x we saw in the very first slide, then if you simply replace mu to be 0 and variance to be 1, so mu is 0 and then sigma square is 1, then it sort of reduces to this very easy density. So 1 by under root 2 pi e to the power minus x square by 2, where x again lies on the entire real line. Alright. Okay, so now a step ahead is to how do you denote the CDF of a standard normal random variable, and again in statistical literature we have a particular notation to denote the CDF of a standard normal variable. So we are talking about CDF of a standard normal random variable. Now this is the notation. So CDF of a standard normal variable is denoted by phi. So phi of x is nothing but 1 by under root 2 pi integral from minus infinity to x, and then you have the PDF here, isn't it? So again, if you remember, how do you define the CDF? So you define the CDF by something like this. So probability that x is less than equal to some value x. Okay. So this is exactly what we're doing. And again, how do you find out probabilities when x is continuous? Through integrals. Okay. So if x is discrete, you find out probabilities through summations. If x is continuous, you find out probabilities through integrals. So in order to find out the CDF, which is nothing but this probability, you integrate from the lower endpoint, which is minus infinity, to x, okay, because the upper bound is x. We want probability that x is less than equal to some value small x, okay. And then what do you integrate? So you integrate the PDF. And by the way, this formula or this relationship we saw in the earlier session, right? I mean, capital F of x, which is the CDF, is nothing but integral of small f of x from, let's say, minus infinity to x there. And of course you have dx here, okay. So this is exactly what we are doing, okay. But now, more importantly, if you have access to a CDF notation, we can talk about all such probabilities now. So let's say probability that x is less than some constant b. So for this, what can be done? So let's say if you standardize both the sides, okay, so you subtract the mean, divide by standard deviation, you do the exact same thing on both sides, so left hand side and the right hand side. So LHS becomes this guy, while RHS reduces to b minus mu divided by sigma. And now if you remember that this quantity is nothing but a standard normal variable, which is z, isn't it? So x minus mu by sigma is nothing but z, which is standard normal. So on the left hand side, you have probability that a standard normal variable is less than this constant, which is again nothing but the CDF of a standard normal variable at that constant. So b minus mu divided by sigma, because eventually this probability would be nothing but probability of z being less than b minus mu by sigma, which is nothing but the CDF function of z. Similarly, one can actually find out probabilities which look like this. So probability that x lies between two constants, let's say a and b. So how do you do it? So again the same thing. So you keep x in the middle, and then you have two constants on the left hand side and the right hand side. So the very first step is to standardize. Okay, so subtract the mean, divide by sigma. So again you should remember standardization throughout your entire life. So what do you mean by normalization, standardization? You subtract the mean, divide by the standard deviation. Okay. Alright, so again if you apply the same technique here, so this middle entity reduces to nothing but a standard normal variable, while you have a certain constant on the LHS and a certain constant on the right hand side. Okay, so you get hold of this equation, and now the moment you have z in between, I can now invoke the CDF notation of z and then write down this is nothing but CDF at the upper point minus the CDF at the lower point. Okay, so this consistency comes from this small equation that probability that a is less than x is less than b is nothing but, or rather is the same as probability that x is less than b minus probability that x is less than a, isn't it? So you take all the values up to b and subtract all the values up to a, and this is exactly what you will get. And then this guy is nothing but CDF at the point b minus the CDF at the point a. Okay, also one more very important idea is that due to the symmetric nature of a normal density or a normal distribution, we can actually get something like this. So CDF at the point minus x, okay, so CDF at the point minus x as per the definition is this. So probability that z is less than minus x, okay. But again if you remember the density curve, let me redraw the density curve. You have a symmetric density curve, and then in the middle what do you have? So in the middle you have 0. By the way, this is the density curve of a standard normal variable, which is z, okay, or rather the PDF of a standard normal variable, so f of z, okay. But then in the middle you have 0, and then now again if you come back to this notation, so probability z is less than minus x, okay. So let's say that this point is minus x here, and then we want probability that z is less than that point. So less than minus x means this area. Now again, isn't this area exactly equal to a similar area on the RHS due to the symmetric property of a normal variable? So again, if I sort of cordon out this area on the RHS, and if these two areas are kind of matching, okay, and then again this would be exactly a mirror image of this guy. So what would be a mirror image of minus x? It will be nothing but plus x, okay. So hence this probability which you see here is nothing but exactly equal to that probability, and now this probability here is nothing but probability that z exceeds x, okay, and I can write down as 1 minus phi of x essentially, okay. So probability z is bigger than x, this guy is nothing but probability that z is less than x, and then you have to do 1 minus that. But now this entity is nothing but CDF at the point x, so eventually you get 1 minus phi of x. Okay. And now all such normal probabilities can be actually found out using a normal table. So in literature we have something called as a normal table or a Z table, and all these probabilities can be found out using a normal table. So by the way, we have a normal table in front of you, and then it sort of seems overwhelming, but then again the first row or the explanation of the table is what? So it gives you the standard normal distribution function or the CDF function of a standard normal. Now very quickly I can actually tell you that how do you find out certain probabilities from the table. So let's say if you want to find out probability that let's say z is less than 1.61, okay. So you want to find out the probability that a standard normal variable is less than 1.61. So how do you do it? So the very first column if you see gives you the values. So which value we want? We want 1.61. So you come down and then you spot 1.6 here, okay, and then the second decimal is 1. So across this row you will see all the decimals. So the very first row if you see gives the second decimal. So 1.60 and then 1.61, 1.62, 1.63 etc. all the way up to 1.69. But then which second decimal we want? So we want 1.61. So we stop here. So the correct answer here is nothing but 0.9463. Okay. Okay, so again reading a standard normal table is kind of easy if you sort of understand that which value should you focus on. And again always remember that all such similar tables you will see, let's say online or any textbook, they either give you the CDF, for example this table gives the CDF, or some of the other tables might give you 1 minus the CDF. So this one point you have to understand, that is the table showing the CDF values or the 1 minus CDF values, and again this is nothing but exactly in the CDF form. So we could directly come to 1.6 and then look at 1.61 and then get the value as 0.9463 there. Okay. So my suggestion would be to practice couple of other probabilities. For example, I will give you one homework. So how about this guy? So probability Z is, let's say, bigger than 2.13. So how do you solve this? So again this table does not give me 1 minus CDF, right? It gives me only CDF. So the very first thing to do is to reduce this. This is equal to 1 minus probability that Z is less than 2.13, and now this entity you can find out directly from the table, and then you simply subtract from 1 to get the final answer. Alright, now we will very briefly talk about an important rule called as the empirical rule for a normal distribution. So what do you mean by empirical rule? I will kind of very briefly talk about that. So again in front of you, you see a standard normal density curve. So again this curve belongs to a standard normal density curve. So what is the important point here is that if you look at the deviations from the mean, okay, so deviations from the mean, so it says standard deviations from the mean. So between mu minus sigma and mu plus sigma, if you look at these 2 points, roughly 68% of the data lies. So let's say if you have set of observations or whatever real data set you have, and then assuming that real data set follows a normal distribution, then between these 2 points 68% roughly of the data set lies or observations lie. Okay. The moment you extend this to one more deviation away from the mean, so mu minus 2 sigma and mu plus 2 sigma, almost 95% of the observations lie. And again if you extend it to, let's say, mu plus 3 sigma and mu minus 3 sigma, then almost 99.7%, which is almost equal to 100%. So almost your entire data set should lie between minus 3 deviations from the mean and plus 3 deviations from the mean. And this is a very powerful property for normal distribution. Let's say if you want to find out certain probabilities, or if you want to find out that whether your process indeed follows a normal distribution, etc., then this rule comes handy. Okay. So between mu minus sigma, mu plus sigma, you know that 68% of the data lies. Mu minus 2 sigma, mu plus 2 sigma, you know that 95% of the observations lie. And lastly mu minus 3 sigma and then mu plus 3 sigma, almost 100% of the observations lie. So this 0.3% that you see, which is not lying in the coverage here, are more like outliers. Okay, are more like outliers. So they'll be either on this side or on that side, kind of. Okay. Okay, so we'll very quickly talk about a simple example. So suppose we test 100 students and find that their IQ is normally distributed random variable with mean 108 and standard deviation 7. Okay, so here my sample size is 100, my mean is 108 and standard deviation is 7. So very simple example, suppose we pick a person at random, okay, what is the probability that his IQ exceeds 115? Now all such answers could be easily found out using simple manipulations of the probability and using the Z table or the normal table we saw. Okay. Okay, so how do you start this? So we want to find out this probability, that probability X exceeds 115. Now the very importantly, very first step should be always to standardize. And standardize both sides. So you subtract the mean, divide by the standard deviation. So here mean is how much? So mean is 108 and standard deviation is 7. So this becomes probability that Z exceeds 115 minus 108 divided by 7, which reduces to probability that Z exceeds 1. Now again remember what kind of a Z table we have. So the Z table we have shows CDF values. So this probability reduces to 1 minus probability that Z is less than 1. And from a normal table, I can actually find out that this value, the probability Z is less than 1, comes out to be 0.8413, and eventually you subtract this number from 1. Okay. So the final answer reduces to 0.1587. Okay. So if you pick a person at random, the probability that his or her IQ exceeds 115 is kind of low, which is 0.1587 only, or 15%. Okay. Alright, now how about this? So again, we will not talk in very detail. So exactly same example, but then now we are interested in finding that if you pick a person at random, what is the probability that his or her IQ exceeds 110 but is less than 115? So essentially, we want to find out this probability. So again, the exact same thing. So you keep x in the middle, you standardize each and every side. So the midpoint reduces to from x to z, a standard normal variable. After subtracting mean and dividing by the standard deviation, and on both sides you have these constants now. So 0.28 and 1. So now this probability reduces to this probability, and now this probability can be further broken down into CDF at the point 1 minus CDF at the point 0.028, and again from a normal table I can find out both these endpoints. So 0.8413 minus 0.6103. So the final answer reduces to 0.231. So again, the more you practice and then looking at a Z table or normal table, the more you will get, more understanding you will develop as to how do you read a normal table, etc. Okay. Now finally, we will close the session by a very important theorem called as the central limit theorem. So you must have heard about the central limit theorem, or in short it's called as CLT, and we will describe very briefly as to what you mean by CLT. So assume that you have a sequence of independent and identically distributed random variables. So x1, x2, x3 up to xn are IID random variables. So we say independent and identically distributed as IID. Okay. So we have the sequence which is IID, and then each has a mean mu and variance sigma square. Okay. Now regardless of whichever distribution my original data follows, but if you have a large n, now what do you mean by large n? Large n means n should exceed 30. This is a convention, it is more like a fact. So large n means n exceeding 30, and then what happens? So if n is large, then the distribution of the sum of all the values, so there is nothing but the sum here, isn't it? So the distribution of the sum of all these random variables is approximately normal with mean n mu and variance n sigma square. And thus just a corollary of this is that if you sort of standardize, if you take the sum, you subtract the mean which is n mu and divide by the standard deviation, is approximately a standard normal variable. And further, just another corollary to this is that one can actually prove that the distribution of x bar is also approximately normal with mean mu and variance, or rather standard deviation, to be sigma by root n. Okay. Yeah, by the way, this is not the variance here, again a small typo, this denotes the standard deviation of x bar. But now just to summarize, what is the important point here is that regardless of whichever distribution your actual data belongs or fits, but if n is large, I can sort of approximate the sample mean. So x bar is sample mean, so I can approximate the distribution of the sample mean to be normal, or I can approximate the sum of the random variables to a normal distribution, which is again a very powerful sort of a rule, right? Because again, let's say if the focus random variable down the line has to be either, let's say, x bar or summation xi, then regardless of whichever distribution your original data set comes from, but then when n is large or when exceeds 30, then you can sort of approximate the distributions of the sum or the sample mean to a normal distribution. Okay. Yeah, so again, just to summarize, a normal distribution is kind of a very standard, a powerful distribution, people use it often, right? And then again in the next week we'll sort of open up the session with, let's say, some estimation, hypothesis testing, and then again we'll see that almost all the tests we'll do, I mean, since we don't have much time, they'll sort of revolve around a normal distribution only. Thank you.